Hi guys, my name is Jeffrey and today we'll be talking about the trends in molecular orbitals of diatomic molecules on the second period of the periodic table. So when I say the second period, I mean the second horizontal row from the top. And diatomic molecules would be two atoms of the same element that would bind to each other. So we're talking about, I have a list of them today. These are all the diatomic molecules I'll be covering today. And right here what I have is an energy diagram where we have two atomic orbitals that can overlap, and these molecular orbitals in the center, which show that all the valence electrons in the two elements that we have available will be able to overlap and occupy these molecular orbitals. And as you can see, each of these molecular orbitals have different levels of energy. As we advance in what we have here is this is similar to one of our s orbitals, and this would be a p orbital. But one thing I'm going to go ahead and demonstrate is that all of our elements will have a full s orbital. So just to kind of display that, all of our elements of our diatomic molecules in the periodic table will have a full orbital level filled up like this, and it's going to be very similar to our 2s, which we'll see in a minute. But I'm going to take this off. But it's understood that this level of energy is much lower than the 2s orbital, but today we'll be only looking at the 2s orbital and the 2p orbital as it's filled. So I'll go ahead and erase this, and we can start taking a look at our first diatomic molecule, which will be lithium. So the first thing that we know about lithium, on the second period, it has one valence electron. So here we'll have, they occupy the 2s orbital. So right here we have two atomic orbitals, the 2s, with one valence electron occupying each one of those atomic orbitals. And as they bond together and overlap orbitals, these two electrons can be seen occupying a bonded molecular orbital. Now the biggest difference, what we need to know for observing the stability of these diatomic molecules, it actually has a lot to do with these bonded and anti-bonding orbitals. When we actually look at the definition of bonding order, it can be defined as the number of electrons in a bonding orbital minus number of electrons occupying an anti-bonding orbital, all divided by 2. Now the higher this calculated number is, we can actually see how strong the bond between these two similar elements is in comparison to some of the other second period tables. But let's go ahead and calculate the bond order here. Right now we have two valence electrons occupying the bonding orbital and no electrons occupying the anti-bonding. So whenever we go ahead and plug this into the equation, 2 minus 0 divided by 2, our bonding order for our diatomic lithium atom, Li2, can be found to equal 1. Okay. So now, let's take a look at the next item, or the next element on the second period, which would be beryllium. So, we're just going to head and beryllium has one more valence electron to occupy the atomic orbital than lithium would. So we would go ahead and add just one more valence electrons, and those electrons would overlap and occupy the anti-bonding orbital. Now this will have a big difference whenever calculating the bond order. We'll go ahead and just observe it now. Now occupying this bond order, this orbital, we have 2 electrons bonding minus the 2 valence electrons that are anti-bonding divided by 2, which we can actually find to equal 0. Now, whenever we have a diatomic molecule with bonding order calculated to 0, it's actually found that these diatomic molecules are not stable or do not naturally exist in nature. So this is not something that you would actually find out and about on planet Earth, and we can say that it's not stable because this calculated bonding order is equal to 0. It's not a positive integer. Typically we can say the formation of a diatomic molecule can happen as long as it's greater than 0. It might not be too stable, something lesser than 1, but the higher that number is, we can say it's even more stable than something that that was at least a decimal or something like that. So let's go take a look at our next. I'll go ahead and write that down. Beryllium has bonding order of 0. Now, whenever we take a look at boron, the first thing that we notice is we have our first set of valence electrons occupying 2p orbital. So we have 3 valence electrons for boron. We'll go ahead and place those right here in the 2p orbital. And as those electrons begin to overlap, we have 2 more valence electrons occupying our sigma bonded 2p orbital. So calculating bond order for our diatomic molecule B2, we can find that 4 electrons are in bonding orbitals, 2 are in the anti-bonding. Divided by 2, our calculated bond order can be found to have 1. So with valence electrons in the 2p orbital, a diatomic molecule of boron can be found to be just as stable as lithium, but capable of formation unlike beryllium. So, moving on, we now have carbon, which will again have 1 more valence electron than our last element that we observed. We go ahead and fill the orbitals like this with electrons not counterbalancing each other due to off-balance principle, rather than having 2 electrons occupy the same orbital counterbalancing. Now, looking at overlaying valence electrons in the molecular orbital here in our pi bonding, we have 2 more electrons that can fill that, and calculating our bond order for carbon 2, or C2, we can find that 2, 4, 6 bonding electrons are present, 2 anti-bonding divided by 2, our bond order can be found to equal 2. So out of all the diatomic molecules that we've observed so far, carbon has the most, or is the most stable out of all the diatomic molecules yet. Moving on, we have nitrogen. Same thing, we add 1 more electron. Pretty much every single time we add 1 more electron to each diatomic molecule, 2 more electrons are added, or overlap in another molecular orbital. So calculating this bond order, we find that 2, 4, 6, 8 electrons bonding minus 2 in the sigma anti-bonding 2s molecular orbital. Our bonding order can be found to calculate 3, which is even stronger than our last diatomic molecule that we just observed. N2 is the most stable by far yet. Moving on, oxygen. We add yet another valence electron. And this will be the first time that we actually see these valence electrons overlapping in the sigma anti-bond 2p orbital. So what this already tells us is that since there are more electrons overlapping in an anti-bonding orbital compared to N2, I can already expect this to be a weaker bond. So let's go ahead and calculate it. We have 2, 4, 6, 8, still the same, minus 4 electrons in the anti-bonding, and this will actually come to be 2 again. So O2 is just as likely to form as C2, stronger than B2 and Li2, but not as stable as nitrogen. So looking at fluorine, we'll go ahead and add one more. Same thing, calculate the bond order. 2, 4, 6, 8. 8 bonding electrons. 2, 4, 6. So fluorine can be found to have a bonding order just as stable to B2 and Li2, but weaker than C2, N2, and O2. So it's still capable of forming, but let's go ahead and take a look at our halogen, neon. So whenever we add these valence electrons to the 2p orbitals for neon, they occupy and overlap in the pi 2p anti-bonding orbital, and I can already tell just by looking at this, because there's just as many electrons occupying the bonding area orbitals as the anti-bonding orbitals, it's going to have a bonding order of 0. We can go ahead and calculate that. We're going to have 2, 4, 6, 8 minus 8, and the anti-bonding divided by 2, bonding order is 0. So there you have it, guys. You can see our non-stable diatomic molecules that we'll have would be beryllium-2 and neon-2. Neon, we can really expect that because it is a halogen, very non-reactive gas, and with N2 being our most stable diatomic molecule that forms. I hope this video has helped you guys and maybe taught you a little something. For more videos for Southeastern's chemistry program, subscribe to the channel at SELU 401.